It's preparing to live stream.
Yep, and we're on. Yay. And we're still got a minute before we start.
Yay, we're recording. So Terry, you're ready for your half hour?
It's a panel session.
Right, it's a panel and discussion session, so as long as I think you're ready. I just figured I'd check.
Yep. I can be controversial for a half hour.
Okay, well, or get other people to be controversial. Shouldn't be hard in this crowd. Particularly on the topics, it should be pretty easy. Just interesting to see who's all here. It's cool.
Sure, also has a Telluride background.
Telluride background.
I figured I'd go the opposite. So this is a Manitoulin Island out in the middle of Canada, like totally flat.
No, I needed to see some mountains.
Yeah, I get that. I decided to use a background in my office. Oh wait, no, this is my office. Sorry.
We should have a picture of the school inside, right? So we pretend we are there inside the room, and we can also buy these fisherman chairs to follow the meeting.
There you go.
No,
that would be cool. But instead I'm actually just sitting in my office on campus. Yay. At least I can do that.
Yeah, no, I'm at home in my kids' room. It's a mess, so I prefer to use a virtual background. So
fair.
It covers.
Yeah, I fair enough.
Hi, Tim. Hi, Tim. Such a long time.
Hello, Chiara.
Hey, Timmer.
Hey, Jen.
It's cool to see you.
Yeah. It's been a long time since we've been in Telluride, huh?
I know.
Yeah.
So, it's one of those next year in Telluride.
Yeah, maybe.
Of course. Unless there's another variant coming.
I just got my first shot of the vaccine, so.
Yay. Okay. And you're feeling okay?
Yeah.
Okay.
We have to accelerate development of virtual reality in case the virus keeps coming back.
Fair point.
Yeah.
So for you that have not been to Telluride, you should know that Timmer is the one who is well known to bring the best tool chest to Telluride. So if you need any tool, like a hot glue gun or I don't know, a soldering iron or anything, you can go ask him, or basically and he keeps a padlock on it. He wisely keeps a padlock on it. Otherwise everything diffuses over the lab.
Yeah,
exactly.
Not anymore, right?
Yeah.
But the Timmer is also the one to know to give the sound to tell us the meeting is about to start. Always appreciated.
Didgeridoo, yeah.
Oh, cowbell.
Yeah.
No, not a cowbell.
It's the didgeridoo, the PVC pipe didgeridoo, yeah.
Mm-hmm.
And he's known for sticking many of these PVC pipe posts around the hallways of the school. These posts turn out to be great ultrasonic reflectors, right?
Yeah.
For the bat sonar stuff. Yeah.
You should see our lab. We've got, some of my students have named the individual poles names like Fred and Bob, and so.
Yeah.
Giacomo.
And you should probably get started, right?
Oh, hey.
All right. Okay, so welcome to the first day of the Telluride workshop. I hope you enjoyed. If you want to get involved, just a reminder, check the Slack website. There are announcements from all of the groups. Get involved. And today our schedule is as follows. We will have in the first hour, the fifth group, the analog neuromorphic technology, doing their introduction, first through a lecture by Jennifer Hasler, one of the group leaders, and then the panel discussion group. Hi, Jennifer. After that, then we go into the lecture schedule for today and tomorrow, and we will have first the SMI group with our lecture will be by Marcel van Gerven, who's also a group leader. And the second lecture then by the TAC group, Veronica Santos. We'll talk about tactile processing. We conclude after 2 hours, and after that, there will be group meetings to be checked out on Slack. So Jennifer, it's your turn.
Okay, so I will share my screen now. Thank you. Everyone can see my screen? Oh, yeah, sorry. It was a good game last night. Anyways. So here we go. Sorry, not quite at the beginning. Let's go there. There we go. Everyone can see my screen?
Yep.
All right, great. So no, first it was kind of neat seeing all the names that we start with and just all the familiar faces. And it's just great to see everybody. I just wish we could all be in person, but I'm still glad we're here. Also, this becomes the introductory lecture for the Neuromorphic Circuits and Tools group, which we also call the ANT group, ENT, and we definitely have the sort of balance in this between sort of circuits and tools that are sort of this group both myself and Terry Stewart are working on. I'm going to kind of go through at least sort of a certain perspective I have on this material and just kind of work through this for a little bit over the next, I guess, 30 minutes. Do that. Sure. Sharing your screen, you can't actually tell what time it is. So I might better make sure I can do that. All right, so I want to just kind of give sort of like my perspective on the sort of neuromorphic circuits and tools perspective and some history and some background and so forth. Kind of when we start off by talking about neuromorphic engineering, of which this workshop has been named and has been going on for multiple decades now, we really talk about this kind of being the sort of connection between neurobiology and sort of electronic and other computation, where one influences the other and then again influences back. There's a lot of different ways to think about it, but I think, you know, I would make the connection back to the sort of the historical starting point at Caltech. Basically coming sort of by three core key people: Richard Feynman, Carver Mead, and John Hopfield. These are names you may have heard of. To which they early 1980s kind of wondered about 1980, trying to figure out, okay, I should try to figure out there's something in between all of these kind of ideas. What do we do? Well, in very Caltech style, say, well, we'll create a class, and by doing it, we'll figure out what it is that we need to know about the material. And so they created a class, and that just kept evolving over the next couple of years, and eventually created this sort of whole area, new major, as well as talking about analog VLSI and neural systems book. Many people in this discussion are very familiar with some of these points, and so it's kind of a neat aspect, and has very much the sense of the hardware-centric nature of a lot of what we looked at. And so most people going, okay, well, for those who don't know much about Carver, there's sort of the quick introduction. I could spend 30 minutes just talking about Carver, but he's known for a number of things, one of which he's sort of the one who named Moore's Law. This was sort of the original graph, or the original sort of VC hockey stick to try to show that everything's going to take off one day. Invented the MESFETs, but also from this basically ended up predicting the very first 180 nanometer channel length transistor 25 years before it actually was in production, and the specs were almost dead on, which is pretty cool. Sort of known as co-invention of digital VLSI, which then also involved a whole bunch of other aspects of developing tools and the tool developments. Because after all, you don't want to be drawing layout by hand, or you don't want to be doing all it by hand. That created a whole infrastructure, as well as the early work on PLAs, which eventually led to the whole FPGA space as we know it today. Carver, it would be remiss for me to say that, he was, I have to say that he was also a passionate teacher and mentor. It's something most people don't know about him other than in this community. And I can say firsthand, it's just amazing to see how he approached it. And then there was this other little field that for many years was just this footnote. Oh yeah, he did some neuromorphic engineering things. But it turns out that there's a lot to that. And there's reasons that there was kind of a footnote to it all. He really spent probably more time on neuromorphic engineering than anything else in his career. Very much had the sort of centric side of having to build things, and very much like if you can build something, you understand it, and if you understand it, you can build it. Sort of derives off some things that Richard Feynman talked about. And so it really sort of like right after all the digital VLSI and everything's there, it's like, well, why not go do some analog stuff and some neural stuff? It should just be straightforward to do. And there was a lot of good work done in terms of retinas and cochleas and neurons and synapses. It created a whole space, which eventually became the sort of Telluride workshop, which was really grounded in the hardware perspectives for a long time. And I think it still is our roots. Created a whole bunch of really amazing people, some of whom are on this discussion. And I'm sure I missed a couple, and I'm so sorry. But the thing is that this really started sort of the next generation of analog computing. It was a sense of, getting away from these sort of approaches you had in the 50s and 60s and saying, well, what can we do now that there's a VLSI approach? The issue was there was basically nothing to start with. There was really no theory, no concepts, no nothing. And as digital VLSI had to build a theory to compete with the analog computers of the 1950s and 60s. And of course, once Moore's law took off, they were in great shape. So it required doing things like creating, the initial circuits in theory, which kind of got developed in some really amazing things, but also a bunch of tools, sort of chipmunk tools, a whole bunch of elements for doing MATLAB, for doing measurement, which is kind of way ahead of the way most people were looking at these things at the time, but it's just what you had to do. Chipmunk tools in terms of building simulators and other layout things. Those of you who have dealt with any of the recent open source tools like XChem, you go, wait, that looks almost the same. And it's amazing how these things have been rebuilt over time. So there's a number of areas in this space. Oh yeah, somebody else came out of the group too. So we'll get to that more. But then the first question is, well, why am I going to think about this sort of analog or physical computing? Physical computing is computing over any real value quantity. Okay, so that would include neuromorphic computing, analog computing, optical computing, quantum computing. All of that is really all in the same space, and actually has all similar roots. Actually, it's rather interesting how this works. But the reason at some point is that digital just kind of slows down. This is one sort of early paper that kind of really sort of showed this, that if you look at the multiply accumulators, in this case it was billions of multiply accumulators per second per watt, normalized out, if you actually looked at various chips, there sort of was almost this wall which no one was crossing. And it was very fascinating because before this you had a very more classical scaling law. And the simple answer is this has still been relatively flat ever since. You still see sort of similar problems all the way through. Going into the details takes a lot there. In case you're curious, the reason it has to do with mismatch that affects both analog and digital things, and we'll come back to mismatch. But based around that was something that sort of, it was originally something Carver and me talked about in 1990, was this fact that, analog could be a lot more efficient than digital, both because I only need a couple transistors to maybe one or two transistors to say do a multiplication versus say 1,000 or thousands of them. And I don't need quite the same signal swing. So that should give me a huge amount of improvement in energy efficiency and in size. And so that's kind of the way, and this is kind of an expansion over that original paper. And if you haven't read, if you need something in your reading list, that original paper by Carver and Mead in 1990 is a classic that's important to read. And so you go, well, okay, how did all this proceed? So again, I said this is a bit of my own perspective on these. So kind of want to start to put some things in sort of timeline of this, is that, you begin to say, well, okay, a whole bunch of things got developed. And in fact, to really understand it well, you usually have to kind of go further back in the history and go, there was a whole early version of neural networks that kind of got shot down by Minsky, quite intentionally, in fact. And then, digital VLSI is in 1980, everything had its next regeneration when backpropagation came up, as well as all of the same things that were happening at Caltech. And there's some pretty amazing things that were happening there. And people were starting to ask questions like, well, how do I start to build all of these aspects? There would eventually be things, again, a lot of times we always think of, okay, everything is just about deep neural networks and stuff. And that happened in the last 8 years, but there's a whole lot more history behind it, including things like DARPA Synapse, and that actually gives us the specs of how we think about crossbars today. But it turned out that one of the earliest crossbars that was done all in standard CMOS were these single transistor learning synapse devices. These kind of created your first crossbar devices. And, they were pretty cool because it really gave you the kind of expansion of analog computation. It actually sort of created the whole space of talking about computing and memory, and really gave you sort of a computational engine to work with. And again, based on a whole bunch of other neural network work behind that. And it would be a long history to get into that. But it also gave the experimental verification of what Carver was talking about in terms of the energy efficiency discussions that we saw. It also led to a whole bunch of things which we call large-scale field programmable analog arrays, something that we've spent a lot of time at Georgia Tech doing, and sort of starting from some very little ones to some slightly bigger ones. They've grown up over the years. And I feel like it's important at least talk about the single transistor learning synapse briefly, because it was sort of that first crossbar structure. It sort of created that initial conversation that if I'm going to build a synapse, because we have so many more synapses than we have neurons, that becomes what can limit an architecture. Now, to be fair, neurons do a lot of other things, dendrites and other computational blocks. You really have to take that into account as well. But at least you got to do this much. And so, the things that you really needed was a non-volatile memory. So like a floating gate element, you need to do a feed-forward computation, which you actually can do a product through this single device. You want it to be as small as possible because you're going to need a lot of them. You also need these to be low power, because if you don't, you're going to be completely swamped up by the power levels. And you'd like to be able to have some sort of signal adaptation and programming and actually not just some capability, you'd like to actually have it be signal dependent. You'd like to be able to do a few other things in terms of being able to program carefully. And this was kind of, like I said, sort of the classic paper at NIPS in '94 in terms of how that came about. There was a couple others in that kind of conversation. You might ask, well, why on earth would I do floating gates? And the fact is I'd love to have a programmable parameter, like everywhere, like for synapses, like for any analog elements. Why do I care about that? Well, one, we're used to programming things. Number two, we have mismatch everywhere, and mismatch for analog is the great killer. For any precision analog, this is what gets you in trouble. And so what's your alternative about doing something like these devices done in standard CMOS? This is one such way to think about it in the layout in standard CMOS. Very traditional, simple way. There's many more clever ways to do this. But what you end up finding is your other alternative is a DAC. And you put a DAC at every single cell. You could do some multiplex stuff, but that also has some similar trade-offs. So we'll just go with this one to start with. And even if you're in an older 350 nanometer process, if you only need 3 or 4 or 5 parameters, that's fine. But as soon as you start needing 10, 100, 1,000, and anything we do neuromorphic needs a large number of parameters, the relative improvement is a factor of 1,000. And as you scale down in process, this actually gets better towards the floating gate side, not worse. So it's an interesting conversation to get into there. And for those of you who are going, well, what does like what would a 6 to 8-bit DAC mean? Which is what I was using for that comparison. Well, that would mean in subthreshold, I have about a 30% shift on say a 1 volt range. You can kind of look at those numbers. I need to get about 12 bits to start getting in the 1% number. I say this because in a lot of our infrastructures we do at Georgia Tech, we actually get better than 12-bit precision. Usually it's 14 pretty regularly. Which makes a gigantic difference when you're building things. The other thing for the hardcore analog people out there, the other thing it does is it really starts to transform the way you do design. It actually enables a lot of the early transconductance capacitor designs that were very typical in the early Caltech perspective, that had really good high bandwidth for given energy and low noise. It also deals with the other questions of programmability, linearity, and offsets, by basically kind of handling it. And so you can get a level of optimality. Long story for the analog people, but kind of can go there. And so what you really want though is not just, here's a programmable array. In fact, I think a lot of people see this today where you say, I'm just gonna make an array of something and then my problem is done. it's not done. In fact, you usually need to be able to go from, say, a sensor all the way to the end computation. So that usually requires a sort of a heterogeneous and diverse sense of things. And we're used to, in these days, talking about things like FPGAs. If you're not familiar with them, they're field programmable gate arrays. And basically really nice because we get configurability that allows you to do something equivalent to a custom integrated circuit without having to go through all the pain of it. Well, there is the sense of field programmable analog array. And the thing that you see is that FPGA is basically routing, logic, and IO. And there's some specializations and so forth. If I look at the analog structure, it's analog elements, logic, and routing and IO. That can be analog or digital. So it's an extension out. So you could argue that an FPGA is sort of a subset of an FPA in a way. And given the way that the FPAs are built today, that certainly is consistent. This is kind of a pretty heavy slide, just to kind of, the main point is to say that yes, indeed, we do have a number of them. This is sort of a core sort of technology that's been built at Georgia Tech. This is a die photo of sort of the core 350 nanometer chip we've been using for, gosh, 7, 8 years now. And it's been used in a whole bunch of different frameworks. In fact, to the point that where there's, pretty much dedicated boards built to this. We use this a lot for sensor to processing. So it's not just doing signal conditioning, but for example, things like command word recognition. This was one first example, first demonstrated in 2015, recognizing the word dark actually out of the sensor input. We've done a lot of different classification tasks since then. There's also a whole bunch of tools. And I want to kind of keep always this thing in our mind of there's always computation and tools, and you cannot get away from this. The computation and tools, and you could also put infrastructure in, is always going to be relevant here. What's interesting is this is about 23 microwatts of power. Do anything close to this digitally, that factor of 1,000 that we talked about from that Carver originally hypothesized is still there. That connection is still there. There's been a range of different demonstrations and a short list of things that also include machine learning. And what you realize really quickly is these are not necessarily just traditional sort of analog signal conditioning, but a lot of other aspects. If you're curious what that actual FPGA chip look like, it actually has elements like a core processor on there. It does have SRAM in it, a whole bunch of DACs and other things, as well as you have analog and digital components all the way through. This always tends to surprise people because you think I put my digital things here, my analog things here, and never shall they ever meet. And you're like, no, that actually turns out to not make sense. And as soon as you say, I want to compile, say, like an analog to digital converter, you very quickly realize I actually want them together. But you actually have to build an infrastructure that actually handles that. There's this whole sense of analog computation in terms of then going, okay, well, given I can do that, how do I begin to think about this further? And we're beginning to start to move into some abstraction of and some higher level questions here in terms of how you characterize these various approaches. And digitally, there's a whole range of algorithms. In fact, I like to think about this, say, if you're doing a numerical analysis class, what are the order of topics? Because it tends to be in the order of the complexity. Going from, say, solution of linear equations to integration and maybe iterative equation solutions, root finding, and then differential equations. But you hope the semester's over by then because you just don't want to do them. They're just too painful. And PDEs are some advanced graduate course for the 3 people who care. But if I was doing it for analog, the comment would be, oh, well, I'd be talking about differential equations first after all the preliminaries. And then work my way through it, even, and then look at things. And eventually things like LU decomposition for solving linear equations is the thing I'm going to try to avoid because that's hard. Might find a good solution. All these things are variable. There's smart people out there. But there are, by the way, some good solutions now talking about for iterative solutions for analog, for AX equal B. And that actually gives you a sense of even talking about the relative energy comparisons and so forth of these approaches. There's also a sense of terms of the numerics, and that turns out to be another interesting question. There's always this sense that digital is pristine and analog is noisy and messy. It's not entirely correct. A better way to put it is digital has really good starting precision, but the numerics can get pretty noisy as you keep processing through. Analog has a lot lower starting precision, but its intermediate numerics, the noise that you generate in between, is actually less, which is exactly why digital solves linear equations and analog tends to solve differential equations. And again, everything eventually still has to be sensors to output. And I just kind of keep that in mind, because solving only one piece of the problem is never sufficient. There is a whole range of things I could get into in terms of talking about neuromorphic engineering specifically. I've been really sort of generic and broad here, and I'm really only going to kind of touch on the very specific things, because we start getting into things like, you can take your floating gate elements, which was originally thought of as a synapse, and really expanded to getting good EPSPs. You can do this by really doing what is kind of knowing the connection between biological channels and transistors, and realizing there's a band diagram that's kind of similar between them, and build things up and actually build predictive kind of structures as you work your way up. That actually is relevant, because the point is not just I want to just build new biology, or new models of biology, which I like doing personally, but also you can use it to solve problems. Things like using dendritic structures to do things like coincidence detection, and that gives you word spotting and does things like hidden Markov model classifiers and so forth, as well as things like doing optimal path planning. And this has some pretty interesting implications. We heard a little bit about this today from Jeff Kirschmar's talk. The sort of foundational work underneath that was actually stuff from Scott Koziel's work, actually looking at this with real Hodgkin-Huxley level neurons, looking at the path structure, and also with a core view that you can prove the optimality of the solutions, which is actually pretty cool. We'll get back to that. So this is cool until you go, okay, wait, some of these chips have like 1 million floating gate elements. Okay, it's better than layout, but I'm still writing machine code. And I think every time eventually you build a successful enough neuromorphic system, and I'm sure Kwabena could say the same thing, and other, Tobi could say this, and other people, as soon as you start getting into this space, the tool, you go, oh my gosh, how am I going to actually make this usable? And you need tools. There's just no way around that. We can talk about all the cool hardware development, but this is kind of relative of all the other things that get built in terms of fundamental concepts and built-in self-test, abstraction, which means calibration, mismatch behaviors where you need that, but then different levels of tools for compilation, different level tools, and even then building the education and theoretical models for these approaches, which is really pretty significant how you have to put that together. So for the FPA structures, we quickly realized we better build a tool set or we're in trouble. This is actually a quick picture of what the tool set looks like, of how it actually works. It's actually all sitting in an Ubuntu virtual machine. And it's actually using Scilab and XCOS, which is sort of open source clone of MATLAB and Simulink. And you can basically take this with a laptop and stuff, and all of a sudden you've got a pretty advanced looking lab. And so you end up getting one tool framework. You can do some simulation, target, and design. Those who are in the ANT group are already starting to understand that there's a lot here. But the cool thing I want you to think about is this is a simple block diagram right here. Is kind of how you think about putting circuits together. And then for the experts, you go, here's the entire tool flow, which is pretty extensive in terms of all the pieces that have to be done to get this right. One of the things that's interesting is people go, oh, that was a cute little block. Like here's a little test structure for C4, which is a simple bandpass filter element. And you go, okay, no big deal, right? Until you start to look under the hood and you go, what's in the C4? Well, it's 2 floating gate OTAs and a floating cap. Well, that cap is a selectable cap. Floating gate elements are a transconductance amplifier with a various floating gates on the front end for the linearity and offset behavior. There's an OTA in there, which also has a floating gate in it for programming the bias current. All of that is just sitting there when you just run this. And oh yeah, and you also forget that there's processor doing the data collection and stuff. There's other references and sigma delta converter on the back end. This is just a simple test bench for a bandpass filter. You have to have this level of abstraction. If you wanted to then talk about doing an embedded system classifier, there's a few more levels. And this is important to kind of start building the abstraction, but there's also that sense in analog that there's no abstraction, and digital is straightforward. And that's not necessarily true. And that gets to the sort of framework that you kind of see. And this is, I think, where a lot of the angst often comes in practice, is because when we look at digital stuff, we have high level, have a Turing machine model. And from there, we have things about, core-to-core blocks, algorithm order, numerics. So when you open up your laptop, like I am today, and you want to sit down and actually do some numerical stuff, all of that's there. And for those of you who are EE or Comp B or whatever, you've been bludgeoned with classes on this. And when you do this in analog, what does it look like? Well, you start off with classically, it's been, here's my model. You go, here's a problem, and people think hard. Real smart people think hard. You go find one or two experts, they think hard. A miracle occurs and out pop circuits. And you wonder, that's probably why it doesn't get as big a following as you would like it to be. And what we've been finding is on the analog side is there's a whole set of pieces and parts you can now build into this. On the algorithm aspects as well, which really gets to the point of all the analog computation is nearly free. And the communication's what costs. And the biggest cost for communication is to memory banks. Avoid those like the plague if you can in this space, because it'll just hurt you in digital, but it really hurts you here because the analog becomes basically free. There is an interesting sort of controversial perspective on this too, because as soon as you start to step into that, you begin to realize I'm computing over real valued things versus discrete valued things. And trying to find the connection between them is hard. What is clear is that if I go from a real value to an integer, I can, if I go from integer to real, I can do that approximation. But the other way is always an approximation and always missing part of it. And what's fascinating is the brain really does seem to operate over these continuous valued structures, and that makes all the difference in the world. And I imagine I created some topics for some people right now. This is fun. So basically how this all comes together is that, in the end, a lot of us care about understanding the brain and understanding the computation of it, and eventually one day building something like it. Obviously, one could go down the path of lots and lots of servers, but to look at the level of computing in the brain is phenomenal. It would probably require about 10,000 of these IBM Sequoias to make this thing go at this point. And those are powered by hydroelectric dams, so that's fun. But every single one who's listening to me, this has been done with about 10, 20 watts, pick your number. But it's also powered by things like this. And of course, being around the Telluride perspective of it, one thing I miss is the fact we all get a chance to eat together and get a chance to cook and do all that. One of my favorites being green chili stew, that shows up a bit. But the thing is, the other way is then how do you start to build this in embedded structures with all of these physical computing approaches? And that really is something that needs all the neuromorphic circuits and tools. And that's kind of what we're looking at there to really sort of take advantage of the energy efficiency below what is a sort of energy efficiency wall mentioned, all the way to what we think at least biological neurons do, but I'm sure they're better than that. So I'm just going to kind of go with that. By the way, a lot of this came through a lot of efforts through a lot of students, colleagues, friends, sponsors. Again, always fun to have people come together. And since we can't do that, I figured I'd pick a couple random pictures of people over the years. Again, I miss seeing you all in person. In case you want some more detail on this, there is a lot more video presentations on a lot of these things. Yes, and I'm definitely in a Telluride mood with all of this. But many different things, both on the FPAs, on these aspects, been trying to put some of these pieces together. Some of them even have some cute animation in them. If you want to read more about the FPAs, there's a recent paper from IEEE Proceedings that goes through all of that. And any other questions are definitely appreciated. I wish we were doing this in person. And then the last part is, I really do want people to please come to the ANT group, and we're going to be talking more about all of these different things as we go. So please do come. And at that, I am going to conclude.
Thank you, Jennifer, for this very informative introduction. And yeah, it's still your turn. You are.
It goes to Terry.
It goes to
Sure.
Terry. Okay.
Well, I can. So I guess the next thing is our panel discussion on this. I believe Kwabena is on the call, or at least was recently. And yeah, I guess our main, and I think we'd also be useful to have Tobi involved in the discussion. There we are.
Yeah, there's many more people here, right? That could also contribute.
There's a lot of people who could contribute. So
we'll just have everybody contribute.
Yeah, I am going to share set of questions, or just sort of things. And yeah, I don't know where even we want to start. I mean, I have certain very specific, strong ideas about what jumps out for me. So I'm just going to go very, very, very briefly and say two big things that jump out. This aspect of differential equations being the building block that is sort of a fundamental difference between digital versus analog is something that, for completely different reasons in the work that I've been doing, we've been trying to build large-scale brain models that are doing tasks. That's been exactly the hurdle that we've had so much difficulty teaching to students. They get so used to programming using digital, but with differential equation, I argue pretty strongly that recurrent neural networks can be best thought of as things that are good at approximating differential equations. So you want to design, build things in terms of differential equations. And that's really hard for people to learn to do unless they have a very specific sort of electrical engineering background. So that's one big thing, to just highlight that aspect of a different way of thinking about programming. Another big thing that jumps out to me that is perhaps so controversial, I will somewhat hesitate to bring it up, but I will anyway. The argument that you're making about, look, we can do a multiply really, really cheaply with one transistor, that kind of gets at like the fundamental reason right now, like the reason that I hear so many people quoting right now of why to use spiking neurons is to make the multiply cheap. And this is a very, very different answer that doesn't require spiking neurons. And so then that starts opening up the question to, okay, are there other things about spiking neurons that are useful? Is it about internal state in the neurons? I did find it very interesting either yesterday or the day before when statefulness was being talked about, people entirely focused on, oh, you make recurrent connections and that's how you get statefulness into your system. As opposed to it being something specific about a neuron itself being stateful. Anyway, I guess all I wanted to say in there is the controversial way of phrasing it would be, hey, does this way of doing multiplication mean that spiking is not useful anymore? Or we have to at least search in order to find out what spiking is good for again. Because in digital, I'm completely convinced that spiking is wonderful for dropping the power consumption down. But I don't know.
Disagree.
Excellent. Good. Do you want to follow up on that?
Agree and disagree. Anyway, it's a different story. Kwabena, okay. You're there, right? Are you there? You're going to show yourself?
Yeah.
There you go.
Here we are.
You're muted now, though.
Yeah, but go ahead, Toby. You were going to say something.
No, go ahead. Did you follow the instructions for the panel and prepare something?
No,
I followed the instructions. I actually prepared something.
Yeah, so please do that. I didn't prepare anything. I'm just extemporaneous.
Okay, I have one simple thing that I would like the CAD design community to do. You have to let me share though, right? Okay,
Yeah,
thank you. It's a very simple thing. And Cadence or Mentor or whoever develops. So how many people actually like to run SPICE? Nobody likes to run it. It's not a pleasurable experience to do circuit simulation. And the reason is really our tools are arcane. The process design kits are arcane. There's all kinds of bugs. The tools are incredibly complicated. Mm-hmm. But there was one beautiful thing that can be done very easily by the design editors that was done by John Lazaro and Dave Gillespie decades ago in their Chipmunk tools. Chipmunk, how many people know this tool? It's completely obsolete now, but all of us neuromorphs from Caltech know it. And you could just drag transistors up on the screen, ground symbol, some voltage source here, and a clock. And then as soon as you had a complete circuit, it would start simulating itself. You didn't have to start anything. And you would see the voltage live. And if you wanted to, you could actually go into this control panel here, and with your arrow keys, you could change the voltage and see what was happening in the circuit. And you could even make these wires glow with a color proportional to their voltage. So you were really like on the lab bench wiring stuff together, interacting with things in real time. And there's no reason that SPICE couldn't do that now. They can't, there's no reason they can't go into the parameters of the models and change them while the simulation is running in an interactive way. Instead, they do this completely brain dead 1960s style punch card.
It's job security, Toby.
Okay, that's what it is. So
Yeah.
By the way, yeah, so you think it's just job security for the people that run these arcane tools?
Well,
I'm going to add in a little more to that. That I also think that that with digital, like there's less need for that interactivity, perhaps in digital. Like the moment we're doing
but
anything with
it's still
differential
needed in
equations.
analog, right?
Yeah,
it's needed in analog, especially for learning things. But the problem is the tools for learning are not compatible with actually chip design.
I agree.
Right.
Yep.
What do you say, Kwabena?
Yeah, I agree, Toby. I mean, of course.
That's one point I was going to make. Okay. So that was one of the questions, right?
Yeah.
Okay, I'll answer another question on this list too, right? What situations have you been in where better tools would have made a difference? Well, I've been in lots of those myself, but if you want to really read all the horror stories about tools and the problems you have with tools for analog design, you see our ISCAS confession session paper for many examples. And I bring this up particularly because the ISCAS 2011 paper, which was called Confession Session, Learning from Others' Mistakes, and the ISCAS 2019 paper, which is called Confession Session, Lessons Learned the Hard Way, had a huge number of co-authors who actually have been at Telluride in the past. All these authors here have been past Telluride participants. And it's basically from their participation in Telluride and of course in ISCAS and the Sensory Systems Technical Committee that these papers arose. So I'm going to post this link here for especially for all the students here. Check out these papers and you can just read them in bed or, while you're sitting on the tram or whatever, and just enjoy these things. Basically, you learn by seeing the mistakes that other people do.
Absolutely.
Yeah. And then what else did I have here? Okay, I'll tell you one story here now related to analog, which is a very recent experience that came out of my longtime love of the Bolton-Gielen current splitter architecture, right? Here's Widlar's bootstrap current mirror that makes a PTAT current that I would use on all the bias generators, on all the neuromorphic chips. And then Bolton-Gielen, came up with this current splitter principle where you put a current in and it's like an R2R ladder. At every stage, you get half the current. I really love this circuit. I just think it's absolutely beautiful the way the current divides across all domains of operation of the transistor in a nice, quite precise way. And so I had the wild idea for the class project of this year's neuromorphic engineering class that we teach to try to do an analog multiply accumulate unit using this current splitter to digitally determine how much current to take. And so the students went at this. They designed a 3200 square micron MAC unit. They achieved in 180 nanometer CMOS technology about 6 picojoules per MAC operation. Not bad, right? But realize this is only a 6x3 bit MAC, right? That's enough to run low precision neural networks, shallow, low precision neural networks. But compare that number here with Horowitz's numbers from decades ago now, it seems like.
Which are mostly simulated.
Yeah, I mean, it hasn't.
Those aren't real.
No, they're real. The real numbers are smaller than this. No, we just simulated. 16-bit
I'm sorry,
multipliers.
Sorry,
just a minute. Let me finish, and then you can comment. Okay. Remember, this is also happening at hundreds of megahertz, and this is happening at about 10 megahertz, or at most 10, more like 1 megahertz. This is at hundreds of megahertz. You can get these energy numbers. The problem with this design that we did, which is just an experiment, it's a learning project for the students, is we are doing this at a single MAC level, and we weren't yet exploiting any physics. We weren't exploiting current summing or copying and things like that. So this is still open. It's still not concluded, but this exercise clearly shows that you're going to have to work hard to beat what digital can do, right? If you really want to do it and get the precision that's needed to really ship things in mass production, which is the only thing that really counts in the end.
Could I say something?
Okay, so now you can disagree.
Okay, thanks, Toby. So, well, first of all, I think a picojoule per MAC is not as far as you can push analog. You can go much deeper if you're doing some clever circuit techniques, right? And so the state of the art is more like femtojoules or even below, femtojoules per Mac, right? And then there was now the second point you made. So
but not in mass production, not in mass production, right?
Sure, no, but no, in deep submicron you can bring it actually down to attojoule per Mac range. If you're using charge mode devices as opposed to resistive, and we can go in detail of what analog techniques you can use here, but so you can get down to sub femtojoule, right? But the big killer in all that is the interfaces, the analog, the digital conversion or the digital to analog conversion that you have with interfaces. And they're the point that Terry raised that, if floating, floating point is, so spiking may actually help here, right? Spiking representations that are reduced amplitude as opposed to, or temporal coding as opposed to deep analog or precision, right? But in any case, so the digital analog comparison is I mean, you don't just look at the crossbar or the multiply cumulative element. You have to look at the periphery, and
you have to get the information in and out, and you have to store the memory somewhere, right? And the only cheap memory you can afford is DRAM. If you're going to store everything on chip, you can maybe fit a little network, but ultimately, if you want to run big networks, you have to put the memory somewhere, and the only thing that people can afford to buy now is DRAM still.
Well, I thought Jennifer,
but you have to be somehow compatible with that.
Yeah. I'm waiting to hear lots of other answers before I jump in.
Yeah, but can we take questions from the audience and stop arguing among the experts? And I think I'm sure people also have some questions for Jennifer, given her nice intro and stuff.
Yeah, although I also do appreciate Toby framing the problem the way you did, even if I disagree. I'm letting others jump in first.
Be shy. This is an area that always should be contentious, right? And the whole idea is to argue for your point of view. So if you have a point of view, this is your chance to argue for it.
I put the question in the chat, but it's just a technical question about your presentation. But so I see that your workhorse chip is a 350 nanometer chip. How far can you actually scale with floating gate? Because at a certain point, the quantum tunneling becomes a problem, right?
No, actually not. I mean, we've actually had really good results measured down to 40 nanometer. We've actually had these structures have gone at as large as was at 2 micron CMOS once upon a time, but it's also gone, 40 and below. We've had measurements from, and we've done design. As tight as 14. I don't see any reason that things will not continue to keep scaling there, and that's not shocking because you can easily buy floating gate memories, which is a lot of your flash structures and stuff that are 14 nanometer today, so 14, 16.
But to be clear,
we can quibble on the details, but there's nothing particularly shocking about that. In fact, people talk about all these stack structures, so there's a whole bunch more that can 3D. I know lots of people like, so which is a good thing. But yeah.
But to be clear, right, you can get your up to 14-bit precision, and you can hold it there while the chip is running over a period
certainly
of how
at
long?
40, we've done extensive tests. We see nothing. Everything we've done a lot of measurements at 40. We see nothing that would preclude us not being able to get the same kind of numbers we do in 350.
But so to be clear, it holds state for how long?
I mean, you still talk in the 10-year lifetime. So what we mean by 10-year lifetimes, it'll typically move 1 to 100 microvolts over 10 years.
Sorry, but that's if it's switched off, right?
No, that's running, powered, whatever.
Really? Continuous operation?
Yeah.
Okay.
Yeah, it works. It works really well. In fact, we've done this. We've been doing these chips long enough now that we've had stuff sit on the shelf for 10 years and went back and checked it, and they were exactly where they were. Okay. So The temperature tests are also true for the 10-year lifetime numbers too. So those numbers are real. We have a pretty good confidence with that, and looking at what the semiconductor industry gives us, that's perfectly reasonable. And that becomes then the workhorse for all the other conversations, right? Like, so we're talking about some of the vector matrix multiplication numbers, which would have been, even when we did the original demonstration those numbers were, I'm thinking it was 50 femtojoules per femtojoules per operation at the time. That was in 2004 when we did that demonstration. So no, I think the analog stuff is quite capable if you're good with it. The vector matrix multiplication is quite good. We actually had stuff ramped to a production level once. I can say that for certainty, that I know it can be done. The killer has always been, what do you do with it? I'm just going to reiterate that comment. It's like, you may, I'm going to put a bunch of DACs or ADCs around it, but you're like, yeah, that doesn't work. And yet there's even companies now. There's a company, Mythic, that's basically all they do, right? They look here, it's a VMM, and then here's some DACs and ADCs, and they still get some actually intriguing numbers, and they're hoping they get it for systems. Fundamentally, though, you have to always get this from sensor through to the analog side, which usually means you're dealing with analog on one side or the other of the computation, and you're doing information refinement all the way through. In those situations, the numbers are quite significant compared to the digital equivalents, and at a level that you can't imagine. You could imagine them ramping to production. I've done some of it with like a company that was called Getronics that eventually got bought by TI. So we definitely have some sense of these numbers, at least in this space. So we know, and continuing to look at those kind of questions, by the way, for other commercial things. Yeah.
Jennifer, thank you for your presentation. I'm sure that there are a lot of people here who would like to follow up on some of the links that you showed in your slides. And this raises a general question about the workshop. A lot of tremendous slide presentations are being given. Is there a repository where all these slides are going to show up so that people can follow up and look at what they didn't get the first pass?
I mean, you can watch, Steve, you can watch the live stream recordings. You can see the slides in the live stream recordings.
Okay.
I think that's all we have right now.
Yeah, but it's harder to find stuff in video. It takes more time. So I think Steve's point is, do we have the actual copies of the slides, textual?
Yeah.
I will set up a repository where if people choose to upload their slides or put links to their slides, I can set that up.
I will be happy to upload mine.
Sure, and if anyone doesn't want to upload their whole slides, if they could just pull out the links that they're suggesting people read or references and post those somewhere, that'd be good.
Put them in the Slack, for example.
Sure, thanks.
We shouldn't go too much longer. I am curious, Kwabena, did you have some, and I'm curious if about your perspective on the use of these sorts of floating gate stuff. Like, for example, yeah, do you agree with this characterization? This is the right way of doing large multiplies?
Jen is absolutely right. I mean, you got 1 terabyte in a 2021 phone, Galaxy or iPhone, and that 1 terabyte is floating gates. It's just that they've gone to 3D, they've gone to these gate all-around structures. It's not, there's no feature size that's less than 40 nanometers in there, but by 3D, it doesn't matter. They started doing this in 2013, and I'll talk about some of this in my talk tomorrow. And so another way to get, Moore's law is about density, per unit area on the wafer. And you can get that by shrinking feature sizes, or you can get that by adding more layers of transistors and wires, which the memory guys are doing because it's cheaper. But it's just the same floating gate that Jen is talking about. And all these things about, it doesn't scale at least. Well, you've got it in your phone. 1 terabyte is not to be sneezed at. Fitting inside a phone in a single package. Okay, so yeah, so she's telling you like it is.
Well, sounds like we don't have any controversy.
And, people create this for the industry is not going to listen to any of this stuff you're saying. They're doing it now. The other point I want to make, and I think Jennifer touched on this, is that you do the multiply accumulate, you can claim all these numbers, and we could argue back and forth. Who cares? It's what you get at the system level. Mm-hmm. Right? And all the energy, whether you're doing multiplication digitally or in analog, it's free. That energy is negligible compared to what it takes to drive a wire 1 millimeter or a couple of millimeters across the chip. And the chips are getting bigger relative to the devices. So it's getting even worse. Mm-hmm. And then the calculation is getting even more free. So
yeah, the arithmetic's free, right? You're saying the arithmetic's free, right? It's the memory.
It's free.
It's all the memory.
I think the arithmetic, particularly when we get into these sort of analog and neuromorphic things, the arithmetic becomes free. I agree with that. Digitally, you can't quite say that, but yeah, you're getting there.
No, it's just a ratio of wires. If your wires are millimeters and your whole multiply accumulate is like less than a couple of microns square, that's just the distance alone is telling you how much energy it takes for one versus the other.
And that's the killer.
And this is getting more and more the case. That gap is widening.
Exactly. And having like large memories in some distance away.
It has nothing to do with large memories, right? Because it's really, the chips are no longer built like von Neumann architectures. Right, GPU is not a von Neumann architecture. Memory and processors are distributed all over the place. The problem we have now is that we are solving problems by having a lot of processors working together. And so by definition, you're going to have to move information around to all these processes back and forth. And so even if memory is distributed throughout, there's no bottleneck, you're still moving much longer distances for all these processes to talk together than you are within a multiply accumulate. So it makes it even worse when you go to these highly parallel systems.
I think we're both more or less. I think we're pretty much in agreement on that. That obviously communication is the key, and moving data around is, you've got to be careful with that. And just again, it is an architectural constraint. You just have to be careful. I think we're both in agreement there.
All right, we should wind things up at that point. Thank you all so much. Please continue conversation in the chat. We should have like 4 minutes of a bit of a break, and then we're on to the next part.
Yeah, good job, Terry.
Thank you, and thanks, Jen, for a wonderful presentation.
Thanks, Kwabena.
Yeah, thanks.
Thanks. Have a good break.
So we meet again at noon here.
4 minutes.
4 minutes.
And while we are on break here, just to remind people, it is still being streamed to YouTube and still being recorded. So as long as you're fine with your casual conversation being, feel free to hang in.
Yeah, Giacomo, I know you might have lost some of your audience, but this is a chance right now to do the promo for the IOP journal, right? While people are still waiting for the next session, in case they didn't get away, if Giacomo's still there.
I think he took off. You can do it tomorrow or just write to him. Could do it before.
I'll just post it. I'll post it on the AND group.
Yeah. Hi, Marcel, you said?
Yes, I am.
All right.
I forgot to stop it earlier, man. It's really hard to remember. Remind me to start again, okay?
Yep.
I think you should start again, right?
Yeah, I would think, yes. Shall we do that? Toby, you have to start the recording.
Let me know just before you're going to start again and I'll start the recording.
Okay, we're starting. Okay, welcome back. We're continuing now with a lecture from the SMI group. Marcel van Gerven, who is one of the organizers, will give a talk on how can the brain match the unreasonable effectiveness of backpropagation.
Yeah, so if it's okay, I'd like to just give a short introduction. Cornelia. So Marcel is professor of artificial cognitive systems, and he has been chair of the artificial intelligence department at the Donner Institute Radboud. Donner Institute Radboud University in Nijmegen since 2017. And he's also the director of the Alice Nijmegen unit, which is a European Center of Excellence in Machine Learning. And the department has the mission to bridge the gap between artificial and natural intelligence. And the research in the department ranges from foundational work in theoretical machine learning to empirical work in neuroscience. And also they are focusing on development of more capable autonomous systems and new machine learning techniques with applications in neurotechnology and healthcare. And Marcel's own research focuses on the development of biological plausible learning algorithms and models for closed loop control of complex systems. And today he will share some of his recent work on developing biologically plausible alternatives to backprop. Marcel, pleasure to have you. Looking forward to your talk.
Thank you, Shichi, for the kind introduction. I'll immediately start sharing my screen. And I think you should be able to see it now. Yes, perfect. Yes. Okay, so what I would like to share today with you is some of our recent work on biologically plausible variants of backpropagation. So as you all, of course, are aware, backpropagation has been the core algorithm for effective training of deep neural networks. And basically it performs gradient descent by passing gradient information through the network. So recent work also allows backpropagation in spiking neural networks using surrogate gradient methods. So in principle, it could be the case that backpropagation is related to how the brain learns to solve certain problems. However, as Francis Crick already pointed out in 1989, vanilla backpropagation is highly biologically implausible. So there are various components of the backpropagation algorithm that don't make a lot of sense from the point of view of the brain. So first of all, it requires symmetric weights in weight updates, and I'll say a little bit more about that later on. It also requires propagation of gradient information, and it's not clear how this is achieved in the brain. Furthermore, it suffers from the blocking phenomenon, which is the notion that we need to basically switch between learning and inference throughout the operation of the system, etc. So the question is, how can we improve the biological plausibility of backpropagation? So in our own work, we have addressed a couple of these problems. So first of all, we addressed the so-called weight transport problem, which I will talk about in a minute. But we also derived alternative learning rules that don't rely on the propagation of gradient information. So today I will focus on the first problem. So dealing with the problem that backpropagation requires symmetric weights in its weight updates. So as Stephen Grossberg pointed out in 1987, there's a big problem in backpropagation, and that's referred to as the weight transport problem. So current algorithms for deep learning seem biologically implausible or impossible because synaptic weight updates at a neuron, so at a single synapse, require access to the synaptic weights of all the neurons which it projects to. And of course, in our brains, we don't have direct access to those downstream synaptic weights. And this is referred to as the weight transport problem. So I'll make that a little bit more clear in the following slides. So this is a standard neural network, two-layer neural network. We have basically two weight matrices, standard setup. This is the forward pass during inference, but during backpropagation, we basically need access to downstream weights. So let's focus on this red neuron in the middle. In order to update the weights at this neuron, so the weight matrix W1, basically, we basically need access to a top-down error signal and the bottom-up input signal. However, if we look at this top-down error signal, this is composed of multiple components, and at some point, basically we need the weights which are related to the neurons in the downstream network. And of course, this is tricky. So here we have this neuron. The synaptic weights basically live at the downstream neurons, but we need access to the strength of those synaptic weights. So how can we do this? So basically, we need feedback weights that are exactly the same, or the transpose of the feed-forward weights. So one way to fix this is to say, well, maybe we just don't care. So maybe we can just use random weights, random feedback weights, and then run backpropagation as usual. So this is referred to as feedback alignment. So this works to a certain extent. However, it does not scale. So it really breaks down for more complex problems. So this is a comparison of the error which we obtain if we run feedback alignment or vanilla backpropagation on ImageNet. And basically we see that the error remains huge for random feedback weights. So this doesn't work. So an alternative is to try to infer the synaptic weights solely from the knowledge of the spikes of the presynaptic and postsynaptic neurons. So we don't have access to the synaptic strength, but we assume that we have access to the spike rates or the spike times of neuron A and B. So this is called synaptic weight inference. If we are able to solve this, we might be able to arrive at a plausible way of inferring the feedback weights. So we are not the first to propose this. There are existing approaches. So this is what we refer to as the Grout method. And the Grout method basically uses inference phases in which neurons are randomly stimulated and their activation is correlated in order to infer synaptic weights. This works reasonably well. However, it's only suitable for rate-based networks. And we are interested in estimating the feedback weights also in spiking neural networks. There's also an alternative approach, which is referred to as regression discontinuity design. And this approach basically casts weight inference as a causal inference problem. This kind of makes sense because we need to do a cause-effect analysis. And regression discontinuity design basically tries to estimate around the spike time what the causal effect is of a certain neuron on its postsynaptic neuron. This works to a certain extent, but it requires a lot of parameters, and it also requires monitoring of membrane voltages. So it's a slightly complicated setup to achieve synaptic weight inference. So what we proposed in our recent work is an alternative approach, which we refer to as spike timing dependent weight inference. This is joint work with Nasser Ahmad, who's a postdoc in my lab, and Luca Ambrogioni, who is an assistant professor in my lab. So this so-called STWI learning rule is derived from a deterministic analysis of leaky integrator fire dynamics under perturbation. So basically, if you look at the paper, we go through a number of steps that allow us to show what a weight inference rule should look like under certain assumptions of LIF dynamics under perturbation. So the nice property of this approach is that it can be deployed for parallel and online updates with minimal computational overhead. And the general idea is that it maintains multiple online estimates of neuronal firing rates through eligibility traces, and it makes use of these for synaptic weight estimation. So let's dive into this a little bit more. So we basically assume that we have the dynamics of fast and slow eligibility traces for a neuron J, and these dynamics are given here. So we basically have the fast eligibility traces, which are shown here, and here Sj is just the neuronal spike train of a neuron. And this is basically capturing the effect of the last spike time. Here we have our slow eligibility trace, and this is capturing a correlate of the average firing rate. So our spike timing dependent weight inference method in the end turns out to be really, really simple. So if we look at this setup where we have a neuron J and a neuron I, so a presynaptic and a postsynaptic neuron, using the fast and slow traces, the synaptic weight inference rule takes on the following form. So in order to infer the strength of a weight between a presynaptic neuron J and a postsynaptic neuron I, we use this expression. So this is just standard learning rate. This is these are the spike trains of the postsynaptic neuron. This is the eligibility trace, the fast eligibility trace of the presynaptic neuron. This is the slow eligibility trace of the presynaptic neuron. And this is just a weight decay with a weight decay term. So we basically update our weights only at those times at which the postsynaptic neuron I spikes. So this is really the basics of our alternative synaptic weight inference rule. So if we visualize this, it looks a little bit like this. So we have our input spikes, we have our output spikes, we have a slow input trace shown in red, we have a fast input trace shown in blue, and we have a slow output trace. So these are the only terms which our weight inference rule depends on, and the only updates basically happen at the moments when the postsynaptic neuron spikes. So if we look at our learning rule or our inference rule, it looks very much like a standard STDP rule. Yeah, so if the post and presynaptic spikes are close together, then we get a positive reinforcement of our weights. If they are far apart, then we get a negative reinforcement of our weights. So what we basically did is we conducted a number of experiments to see how well this approach works compared to the current state of the art. So we used a spiking neural network consisting of 100 input neurons and 10 output neurons. And we basically stimulate 20% of the input neurons at random. So the forward weights are just drawn from a normal distribution, and the task is to infer the weights Wij from the spikes of the input neuron J and the output neuron I only. And we compare against the previously mentioned Grout and RDB methods. So of course, we also need to describe the neurons we have been using. So we basically use standard LIF neurons, which are shown over here. We use conductance-based synaptic kernels, which are shown over here, which is basically kind of modeled by a double exponential. This is the Heaviside step function, fairly standard. So when the voltage reaches a threshold, then an action potential is recorded and propagated, and the membrane voltage is reset. So this is our neural model, and these are the results if we compare the alternatives with our STWI rule. So what we see here is the inferred weight compared to the true weight. So these are the results for the RDD method, these are the results for the Grout method, and these are the results for the STWI method. So of course we can also correlate the true weights with the estimated weights, and this is shown over here across time. And basically what we see is that STWI performs quite well. It matches the performance of the Grout method in this case. But interestingly, we can also look at the sign accuracy, so whether the sign of the weight that is inferred matches the sign of the true weight. So if we look at that quality metric, then we basically see that our STWI measure or method does much better compared to RDD and the Grout method. So these are very specific results obtained under a sparse stimulation regime. We also find it very important to look at other regimes, because this is an assumption we are making, and it could very well be the case that if we use different stimulation regimes, that the results turn out differently. So we also compared this approach under a dense stimulation regime. So 100% of the input neurons are stimulated all the time at random. Again, we have the same kinds of results. So we have the true versus the inferred weights. And it's interesting to look at the Pearson correlation and the sign accuracy. So what we basically see is that STWI outperforms the other methods on Pearson correlation. And now suddenly the Grout method matches the performance of the STWI method. So the methods that are being described in the literature, their performance is really dependent on the specific stimulation regime. And we think it's important to take that into account. So what we can also do under the 100% stimulation regime is to create correlations between the inputs. So we can make the inputs perfectly correlated or perfectly uncorrelated or anything in between. So if we do this, then we basically get different results again. So we basically see that all the methods do relatively well. And the RDD method seems to do a little bit better in the medium correlation regime, especially if we look at sign accuracy. So under low correlations, STWI and Grout tend to do pretty well. In the medium correlations, the RDD method tends to do pretty well. So this is kind of showing that a very simple synaptic weight inference rule that is very similar to standard learning rules allows us to get very accurate estimates of synaptic weights. So we also aimed to get a theoretical motivation for our approach. So in the paper, we dive in a little bit more, and we show that if we use a slightly simpler neural model, then we can do a stochastic process analysis. So we can basically compute the base optimal result for that neural model, and then compare this to the STWI rule we have just described. So what you can see is that, yes, the base optimal approach is more efficient in achieving high correlations, but we also see that the STWI rule nicely starts to converge to the base optimal setting, which is exactly what you want to see. So concluding, this STWI rule outperforms computationally more expensive alternative approaches across a wide range of parameter settings. The rule is derived from a deterministic analysis of an LIF neuron. We do make use of a few approximations to generalize to weight inference under noisy dynamics. So there are some approximations in our derivation that are needed in order to make the approach stable under noisy regimes. And we also showed that it corresponds to a base optimal model for simple neural models. So we were able to show this for a simple neural model. If we really want to show this for more complex neural models, then we enter a slippery slope, because then we have to start to perform a non-trivial hitting time analysis of an Ornstein-Uhlenbeck process. And as far as we know, this is an unsolved problem. So there's still some work to be done. So what I hope to have conveyed is that STWI is an effective and biologically plausible approach for solving the weight transport problem across a range of network models and stimulation protocols. And what we hope and think is that STWI might be a key ingredient in the development of future biologically plausible approximations of backpropagation. So I think I'm exactly on time. So thank you for your attention, and I'm happy to take any questions.
Thanks, Marcel. I think you're ahead of time. Okay, so let me see if there's anything in Slack. So I'll just ask a question from Slack, Marcel.
Sure.
Unless you also can see it, the question. It's under the questions channel. No? Okay. So does STWI suffer from the dead neuron problem? That is, neurons from deep layers never fire because spike frequencies drop dramatically after 1 or 2 layers?
That's a very good question. So the analysis we did here is really restricted to input and output neurons. So we did not do the analysis for very deep networks. And it's an obvious step to take in the future. That being said, we are using the STWI rule as the basis for new learning algorithms that actually make use of this weight inference mechanism. I cannot say a lot about this because it's relatively new, but what we see there is that those approaches also allow us to train deep neural networks. So in that sense, I would expect that the approach is actually robust to that problem.
Okay, and I think we have time for one more question. So the other question is, how are the true weights obtained?
Oh, so it's simulation analysis. So we basically randomly generated forward weights. And the learning problem here, so the weight transport problem here is, if we know the forward weights, can we actually infer the forward weights solely from the spike times? So the forward weights, this is ground truth, but we don't have direct access. We only have access to the spike times.
Okay, all right. And then, 2 more questions. Do we have time, Cornelia? So
Yes,
Emre,
we do.
We do. Okay, so another question. Do the synapses need to maintain 2 weights? I don't get that.
No, they don't. No. So they don't need to maintain 2 weights. So they just need access to the pre and post synaptic spike times. So basically, if the feedback weights would convey the postsynaptic spikes, then this should be sufficient for inferring the feedback weights.
I think Emily, I think you're probably asking about the two traces. Is that correct?
Yeah, so there are two traces.
He answered my question. That's fine.
Yeah.
Do you want me to ask that question? So since you showed the example of feedback alignment in the beginning, saying that it doesn't scale, but I mean, because you have an imperfect approximation of the symmetric part, the symmetric, the weights in the other direction, how do you think that's going to affect the gradients and the learning at scale?
Yeah, so we do have a couple of approximations in the derivation, which is needed to be stable against noise. Yeah, so referring back to the previous answer, we have been training approaches that are similar to this weight inference rule on deep neural networks, and there basically we can show that we can scale. So my expectation is that this approach generalizes to deeper networks as well.
Okay, all right. So I guess we've reached the time. Thanks, Marcel.
You're welcome.
For the lecture, it was great. Yeah, and Cornelia, you're taking over.
Yeah, thanks, SMI group. So we're moving on with the TAC group, the tactile sensing. Chiara wants to say something.
Hi, yes. So this is the second lecture of the TAC Sensing group, and I'm really happy to introduce Veronica. So Veronica Santos is a professor in the Mechanical and Aerospace Engineering Department at UCLA, and she's the director of the Biomechatronics Lab. She did moved a lot during her career. She studied at Berkeley and Cornell, and then worked at University of Southern California and Arizona State University. She has a wide research interest, and she's working on tactile sensing, on control of hands, and on the interaction between human and machines. And so it's my pleasure to give you the floor, and looking forward to your presentation.
Much, Chiara. Can you hear me okay?
Yes.
Okay, great. Let me get my screen sharing going. Slideshow. And let me hide a bunch of these things so I can see my own screen.
Yes, we see the screen. I think everything is working.
Okay, perfect. So this is my first time, quote unquote, at Telluride. I'm excited to be a part of this program, and thank you for the invitation. My talk is going to be pretty high level. I'm going to go under the hood a couple times, but I wasn't entirely sure about the varied background, and so I thought I'd give you a fun video-laden overview of the types of things that we do in my lab and the way that we think about tactile sensing, tactile perception, and how the sense of touch can enhance robotic systems. So I'm going to show you only one slide on what we're doing with human subjects. Most of the talk is going to be on tactile sensors and tactile perception algorithms, and then I'll finish up showing you how we leverage sensorized robotic systems to advance grasp and manipulation. So I want to thank Dr. Takor for giving a really nice overview of the richness of this field of tactomorphics, which is actually a new word I just learned on Tuesday. And of these many things that we could build our careers upon, these are the three things that I'll be touching upon today: tactile sensor design and tactile perception algorithms, and how they're incorporated into artificial hand systems to provide information, actionable information for decision making and action. So this is my one slide where I show you a brief overview of the types of things that we do with human subjects. We strive to characterize how humans grasp, manipulate, and perform different tasks such as haptic search and granular media, not because we want to be enslaved by the biological solution, but we see it as an inspiration for ways that you might want to design control algorithms for robots. So in the upper left-hand corner, you see that we've used haptic displays to study the reactive grip responses to unexpected perturbations. We've also sensorized objects to look at the force domain coordination across multiple digits for activities of daily living, such as pouring. We are still going through data on an object handover experiment in which a sensorized object is being passed back and forth. And we're looking at it not only from a kinematic perspective, but also the mutual grasp profile period during that handover. More recently, we've gotten into eye tracking and combining that with physiological sensing, motion capture to try and infer human intent from where the eyes are going. And if we can infer that intent a little bit in advance, then we can design control algorithms for our robots that make for more seamless human-robot interactions or assistive actions. And then finally, one of our more recent studies has to do with studying how humans find buried objects. And so we really, lose the ability to track what the hand is doing or where the object is when you don't have a direct line of sight, as when you're plunging your hand into opaque sand. And so we had to develop things like IMU-based sensor networks to track hand pose without a line of sight. We sensorized objects to track their motion and the forces being applied on them as they're being discovered. But most of this talk is about the sense of touch. And so I might be preaching to the choir here, but I like to say that the way that we think about it is that the sense of touch is vital for any system in which humans use machines to manipulate their world, whether those are machines working within the human body, machines that are intimately connected with the human body and become part of the human body, machines that are close to the human body and still within the workspace for assistive technologies or manufacturing, and even robots that are very far away and remote and are being teleoperated for the handling of dangerous materials, search and rescue, or maybe preparation of other planets for humans. And of course, computer vision is highly valuable and it's great for planning, but there are a lot of times when this visual feedback is either limited or entirely absent. And so this is just an array of different scenarios where the sense of touch becomes, the complementary sense of touch becomes especially important. So there are tasks where you just do not have a direct line of sight, or the hand itself occludes the finger object contact that you seek to control. Or maybe you're reaching in the dark behind obstacles or inside your pocket, for example. Now we're starting to look at a large, section of the community is starting to look at the manipulation of deformable objects. And these are objects for which we may not have models of. And in the extreme, imagine these deformable objects are now animate and you're not entirely sure how they're going to move. How can the sense of touch be coupled with proprioception and audio feedback and visual feedback to safely interact with these animate objects? So I'll show you a little bit of the tactile sensor design that we've done. This is a long-standing collaboration with Jonathan Posner back when we were next-door office neighbors at Arizona State. He did microfluidics, and I was interested in tactile sensing, so we came up with this design of a microfluidic normal force sensor skin that uses a eutectic alloy of gallium, indium, and tin as the fluidic paths, the fluidic wires. And where you see these wire paths crossing over one another, they create a capacitive taxel, which is the tactile analog to a pixel. And this sensor was our first iteration that we'd done together, and because of its design and its capacitive nature, it really only sensed forces that were normal to the skin. And we wanted to go beyond that and also look at shear force. And so we moved from this capacitive-based approach to a resistive-based approach, now creating micro-scale fluidic strain gauges. And taking a cue from Yonglei Park's work on spiral channels for sensing normal forces, we miniaturized that and use spirals for our normal force sensing, for isotropic sensing. Then we also created serpentine channels. Those are the rectangular ones in the upper right-hand corner. And by carefully placing pairs of these, we can use the asymmetric measurements to extract shear. And so one of the bonuses that we realized when we moved from a capacitive to a resistive-based approach is that now we were highly sensitive to vibration. So we found out that we could actually sense vibrations up to 800 hertz. We weren't trying to beat the human fingertip, but it turns out that does exceed, the 400, 500 hertz of bandwidth of Pacinian corpuscles. And right now we're currently developing this skin even further, but making an entire fingertip and making sure that it can be used underwater at depth. So sensing under hydrostatic pressure and in a lubricious environment is entirely new for us and very exciting. This is one of the under the hood slides just to show you, the normal force calibration along the top. We've done a static calibration. The dynamic calibration shows you how sensitive the sensor skin is compared to human skin from a 2012 paper in the literature. And on the bottom, we can see that we have some cross-axis insensitivity, and that you can actually, if you have two different pairs of shear force taxels, you can use those kind of as the basis vector for shear in the plane of the skin, and then use components of those to pick out a 2D shear force vector. But we also have a lot of experience with low-cost, highly scalable tactile sensors. So we've collaborated on piezo-resistive fabric sensors. We've also taken a cue from Rob Howe and Matej Chaukarli and embedded barometers in elastomer. But you'll notice that these are for very large-scale sampling of forces. These are not currently miniaturizable for the fingertip. In the lower left-hand corner, we have an example of a collaboration with Ted Adelson at MIT. We're using their GelSight camera-based tactile sensor, and this sensor has a small cell phone-style camera embedded behind an elastomer pad that has a highly reflective inner surface. And if you put a series of dots on the inner surface and track the optical flow of those dots, as well as the change in color from the internal illumination, you can back out information about the local geometry, the forces being applied, the shear, the torque, and all that. But what you'll see in most of this talk is this green fingertip. This is the Syntouch Biotech. This is what I worked on when I was a postdoc with Jerry Loeb at USC. And it was funded by the DARPA Revolutionizing Prosthetics Program, intended for prosthetic hands. It was bio-inspired in that it has a rigid core like the bone in your finger, an elastomeric skin inflated away from the core by a conductive fluid. There's also fingerprints built into the skin to amplify vibrations that are picked up by a pressure sensor embedded in the core. So we basically have a hydrophone that we can sample slowly for a crude measurement of overall internal fluid pressure, or very fast to pick up on transients and vibratory signatures associated with texture. On the surface of the core, we have electrodes, and we can use that spatiotemporal information about the overall deformation of the finger pad as it relates to local shape and shear and things like that. And then finally, there's a thermistor in there, and you can use the rate of heat conduction away from the finger to infer material properties, although we use that less than the electrodes and the pressure sensor. And of course, all of these tactile sensors I just showed you are highly deformable. We don't have analytical models of them. They don't come with convenient calibration matrices like our rigid force torque sensors. And so we rely heavily on machine learning, but for pattern recognition purposes. So we take a cue from the 1980s literature on psychophysics of exploratory procedures performed by humans when they want to extract information such as weight, shape, texture of objects. And we basically play these exploratory procedures out on our sensorized robots, take this rich multimodal tactile sensor data, and then in this case, we use support vector machines to classify edge orientation, the size and shape of different bumps and pits. More recently, we've used convolutional neural networks to leverage all this these amazing computer vision algorithms that were developed before it was ever applied or I think thought about for tactile sensation, which is to create tactile images. And the electrodes that we're working with the biotech, we're not in the hundreds or thousands of taxels. We're talking 19 taxels. And so what we have to do is we take this 19 set of taxels, we unfurl it onto an imagined skin, and then we interpolate, assuming some continuous deformation of the entire finger pad, just to get these quote-unquote tactile images that we can leverage and put into our convolutional neural networks. So what you see here is a real-time demonstration of the inferred tactile directionality based on the shear and finger pad deformation. And you can use this information to make for more seamless interactions between the robot and a human for handover, for example, or even the robot and the environment. Say you're setting a wine glass down on a table, and you want to do that without relying on solely computer vision and a perfect model of yourself and the table location. Things get really interesting when you consider tactile perception within granular media, because unlike the examples I showed before, where you're measuring the gradation of contact in an open air environment, as soon as you take your tactile sensor and you plunge it into a medium that is going to stimulate the vibration modality, the finger pad deformation modality and all that, now the problem becomes, how do I pull out, how do I distill the information I actually care about from all this other noise in my tactile data? And so what we did for this experiment was we took one of our 7 degree of freedom robot arms, sensorized with biotech sensors, and we raked it through different types of granular media, and knowing the kinematics and the location of the object, we could create models of the tactile state. When is the fingertip actually touching a buried object that is of our interest, and when is the fingertip simply moving freely through granular media? And one thing I'll say about this approach and the biotech sensor is that I'm not claiming that we need all of these complex and additional modalities of touch, but we have these sensors, we can collect this rich data, and then we can play ablation studies after the fact to investigate which of these modalities is most useful for certain types of tasks. So we trained a perception model on the large cottonwood balls that you see on the left-hand side. And then once we had that model, we played it out for a variety of different aggregate types of particles, ranging from poppy seed to mimic coarse sand, all the way up to wooden beads for coarse gravel. And this is the pipeline that my student came up with, which is to begin with the biotech sensor. We look at the vibration and internal fluid pressure signal from the hydrophone, and we perform empirical mode decomposition so that we can extract some of the oscillatory signatures within these data, but still remaining in the time domain. And then we take all of the 19 electrode impedance values and we create feature tensors with all of this multimodal information. We fuse the different modalities, and then we create a sparse coding over complete representation. That's this 400-dimensional sparse representation. Purposely over complete, the sparse representation allows us to do computations faster, but also enact autonomous feature extraction algorithms that we can then send to a recurrent neural network that can separate these data into the 2 tactile states that we care about: contact with a buried object or movement through granular media. And once we have this model, then we can build belief maps, where the belief maps are probabilistic visualizations of tactile data. This is something that I'd love to talk to someone about, ideas on how do you visualize the sense of touch for an operator who may not be wearing a device to provide that haptic feedback directly. And so going back to this experiment, you'll see in this example the tactile perception pipeline running just for a single stroking movement of the finger, and we can already start to build a belief map and have probabilities of where we think something might be buried, and then we can use that information to plan the next exploratory action to reduce uncertainty in that belief map. Now in the upper right-hand corner is an example of another project we're working on to develop a model of granular media jamming. So one of the things that's unique about working and moving within a granular media environment is that these particles can flow, and they can also build up force chains. And so ahead of the fingertip, you'll see these little white particles that are just taken by looking at adjacent images in this video. So we're highlighting the particles that we think are moving ahead of the fingertip. And as this front of particles approaches the buried object in blue on the right, you'll see an increase in the perceived fingertip force from our tactile sensor. And this is a false positive because we're not actually making direct contact between the finger and the buried object just yet. What we're feeling is the force chain, the force moving back from the buried object through this force chain of particles to the fingertip. And so if we can have a better idea of the effects of fingertip depth, fingertip speed on this added uncertainty in our force sensation, then we can combine that with our tactile perception pipeline on the left to further reduce uncertainty in the size, shape, and location of something that's buried. And this all fits within a grander vision where our contributions would be on this perception, the blue perception block, but we envision a full action perception loop. Whether on the action side, we're driven by robot semi-autonomous behaviors, or it's a high-level human supervision, or even very manual teleoperation of the robot, that someone is deciding the action that the sensorized robot should take. And then the raw sensor data comes in, we run our tactile perception algorithms, and then we spit out, in this case, a visualization of where we think something might be buried and send that information back to the operator. The idea is to use touch to produce actionable information so that someone, whether an algorithm or a human, can then make decisions based on that value-added information. So the last topic that I'll talk about is the manipulation of deformable objects. And so things get a little more challenging when you are trying to grasp and manipulate a deformable object with a deformable tactile sensor and do it in a model-free manner. And so in this experiment, it's about 3 years old, but I did want to show you some of the things under the hood because it was our first foray into the manipulation of deformable objects. This experiment is all about functional contour following. So how might we, with our eyes closed, be able to close the zipper on a Ziploc bag using touch and proprioception? So we used our 7 degree of freedom robot arm again. We have biotacks. We have it the fingertips squeezing the Ziploc bag, and then we're going to move the robot in a plane along away from the tether point of the Ziploc bag. You'll see that we have a video camera there. We use the video camera to automate the policy search process, but once the policy is learned, you can turn off the camera and you can actually perform the task with touch alone. Now on the right-hand side, states, actions, and rewards are highly important for reinforcement learning. So first you have to figure out what are the states that you care about. And in our case, we cared about 3 tactile states. Those are the high, center, and low. And the definitions of these things come from our physical intuition. You know, that's a pro and con of doing this type of work. But I guess it makes it so that humans still have a place in this world, because I think that the art of reinforcement learning is really the crafting of the reward function. And so in this case, we're considering the state of the fingertip relative to the zipper, shown in blue. And that zipper can be low on the fingertip, centered in the fingertip, which we think, you know, or we designed this to be good and of high reward, or very high on the fingertip. And then on the bottom, we have actions. And this came after a preliminary study where we did try actions that were you know, equally spaced across the 180 degrees, but we found out that these 5 were really useful for exploring our ideas. And so those 5 directions are the 5 things that the robot can do when they're grasping the zipper. And then after that action, we look at the raw data that we get from our tactile sensors and decide whether to reward the robot for taking that action or not. And so in this particular paper, we were comparing our contextual multi-armed bandit approach to a benchmark Q-learning approach. But just briefly, multi-armed bandits, that phrase comes from the nickname for slot machines in a casino. So imagine you've walked into a casino and you're presented with a huge array of slot machines or multi-armed bandits, but you only have a fixed amount of money. The question is, where should you spend your cash? Well, this is the constant battle between exploration and exploitation in reinforcement learning. First, you need to explore a little bit. So try your money in a few of the different slot machines to see which ones are kind of hot, which ones are going to pay out. And once you get a good idea of the landscape of which machines are going to pay out for you, then you begin to exploit that policy and play only on those machines. And the contextual component means that we are taking into account our current state and trying to more efficiently balance this exploration versus exploitation. The Q-learning on the left in this example had fixed parameters and a fixed rate of exploration. So what you're going to see is on each of these pie charts is a state. Either the tactile state is high, center, or low for the zipper relative to the finger. Each of those pie slices is one of the 5 actions you can take from that state. And then the numbers on the outside are the number of visits that the robot has made to these particular state action pairs. And along the bottom is our reward function. So you want to see actions, a lot of time spent where things are orange, because that's where you get the major payout. And so in this example, we were running, about 750 iterations where the robot is learning through its embodiment where it should spend its exploration and exploitation time in order to perform this task. And so one of the things you'll notice by just looking at the numbers outside on the right-hand side with the orange slices is that we have spent more of our money, our resources, and think of this in lab terms, right? This is your student time. This is your robot hardware time. This is wear and tear on your sensors. And you can actually wear out the tactile sensor skins. So, unlike computer vision where you can go online and download millions and millions of images to learn, for the sense of touch, we actually have to run, unless we have good simulations, we actually have to run our robots to collect these data. So we were trying to do this in the most efficient way possible. And this is showing the learned policy being played out on a different bag than the policy was learned on. It's more flexible, it's got objects in the bag and so on. We're also currently finishing up a paper on the manipulation of deformable sheets. And again, the difficulty of this is in crafting the reward function. How do you craft a reward function that is tactile sensor driven for the task of, for example, turning a page without excessive jerking of the page or warping of the page, or however you want to craft, the good and bad of your task? And then on the lower right-hand corner, we're about to submit a paper on 2 novel controllers that we've designed to manipulate in a tension-driven way deformable linear objects such as fishing line, rope, cables, and so on. And again, the theme here is that as soon as the rope gets taut and gets straight, computer vision is not helpful for inferring the gradation of tension in that rope. And so in this case, we're not using tactile sensors, but we are using a wrist-mounted force torque sensor. And depending on the desired force trajectory that's commanded, or the force magnitude and maybe human demonstrated motion, we can control the wrapping of a rope around a horizontal post or the wrapping of a rope around a boat cleat. So that's all I really wanted to show you, but in the spirit of this open discussion and this fun Telluride forum, I thought I would just throw in a couple summary slides of, for better or worse, no judgment, these are the things that we tend to do in our work. And so you'll notice that we have completely embraced deformable and multimodal tactile sensor designs, with the exception of camera-based tactile sensors where we have many, many pixels to work with. We really try to make the most of the few taxels that we have. In some cases, this is 19 taxels. We really leverage continuous skins. So as opposed to treating every taxel as a discrete unit, we like to embed these taxels into continuous skins because it enables us to, as long as we're encoding the features that we want to extract, the features that are useful for decision making, I'm not so concerned about the total number of taxels that we have. And we really leverage mechanical coupling. I know if you want to do high spatial resolution, maybe the mechanical coupling is not so beneficial, but we like the fact that this skin stretches as a continuum and enables us to get information about finger-object contact, even from areas of the skin that are not directly contacting the object. So for example, if you put shear taxels near the nail bed, just like your own fingertip, if you press down on a table and move your finger left and right, you can actually feel strain near your nail bed, even though that portion of your skin is not contacting the table. And we leverage all of that information. Of the different modalities that we've looked at, we have found that we get the most bang for our buck in terms of finger pad deformation. Highly useful for edge orientation, bumps and pits and other salient geometry. The tactile directionality is coming from the deformation of that finger pad. Even the granular media, tactile perception, we are leveraging the hydrophone data, but in our paper, we do an ablation study where we knock out different modalities and find that if you did have to give up one modality, you would want to give up the hydrophone because you can still do good tactile perception with that finger pad deformation data. And also, without analytical models of our tactile sensors, we rely heavily on machine learning for pattern recognition. And more recently, we've been using recurrent neural networks so that we can leverage not just the static spatial patterns, but also the temporal changes in space over time. We have found that the art of reinforcement learning lies in this design of a task-specific reward function, and there's a pros and cons for that, right? It depends on your application. If you really want to do one thing really well, you can design a system for that. If you're interested in the robotic system that generalizes to all tasks ever, over all time, we have a long way to go. We're nowhere near the generalizability that the community seeks. And finally, what we've found is that we've actually had to reduce the dimensionality of our tactile sensor data. Even though we might be starting with only 19 electrodes, in order to practically implement this with the reinforcement learning and all the different parameters that you could tune for and optimize for a dynamic motion primitive, for example, that we used in the page flipping tasks, we actually had to reduce the dimensionality to get a representation of the tactile sensor data that could easily map to the states that we were interested in and rewards. If you cannot distinguish between the different actions that you take and the different consequences of those actions, then reinforcement learning becomes nearly impossible. That's been our experience. So I'd love to chat more during the Q&A, but none of the work I showed you would be possible without our amazing students, collaborators, and funding agencies. Thank you so much.
Thank you, Veronica. It was really inspiring, and you really gave a lot of different ideas about what it means to work with in the tactile domain. I think we are all mostly working with vision, so changing domain also has its challenges and peculiarities. So I saw that there are a few questions on the chat. Mm-hmm. Let's see. So I'll start from the kind of the last ones and then go back if we have time. Cornelia will keep us on time, I think. So from Tobi, you mentioned shear force quite a lot, but not sensing slip of held object. Is that considered difficult still, or is it solved?
Well, I guess there's slip after the fact, and then there's incipient slip, which is just before when you really want to have that reactive grip force. I wouldn't claim that incipient slip is necessarily solved. We did look into it with one of our earlier tactile sensor skins, and I think it is also important, but maybe on a different time scale. So it depends on whether you want to impose some reactive reflex, like a safety reflex, or you're trying to gather information for a higher level decision-making process. And that's where, tactile directionality would be at the higher level, and then just gripping harder because you sense that the object is about to slip would be at the lower level. So I think that there are still people who are focusing on this incipient slip detection.
And then there's another question from Cornelia, and I have a similar question. So she said, you are using very little information from the Syntouch sensor. How detailed information should we expect from this sensor or tactile sensors in general? For example, accurate location, as in braille reading. Oh yeah, thanks. So, and I think this is also links to my question, that is, you said you kind of try to use the less information as possible, and use it in the best way. But is there something that you think it's missing, something you would like in a tactile sensor that still is not there?
Well, I think if we had a tactile sensor that was as amazing as human skin in terms of you know, the richness of information, the density and the coverage, that would be amazing. You know, I'd love to collaborate with others on this at the symposium who are developing these neuromorphic skins, because we've never had the privilege of having such fast response all over the hand. I mean, we're talking fingertips in my talk, but I would love to have entire gloves, have the whole body of the robot or the human sensorized. There's a whole nother subfield of whole body interaction between humans and robots. And so these are some of the things that we haven't been able to look at because we've been, you know, constrained by the real estate of the information that we're getting.
Right. So basically, you think that the neuromorphic thing would help in covering large areas because of the problem of the thousands of data that we have to sample. But what about the materials? You know, you mentioned at the beginning the capacitors and then the resistors, and actually there was the first question from Tobi was why the resistors are have higher bandwidth, can sense vibration better than capacitors. So to me, on our robot, we have capacitive sensings, and I know one of the bottlenecks is the 10 millisecond sampling, but that's not related to the capacitor, it's related to the readout, right?
Good. So yeah, you've touched upon there's actually two things. One I didn't mention, but you're highlighting, which is the mechanical properties, right? The hysteretic properties of whatever viscoelastic material you're using, that's going to impose some time delay for the you know, the recovery of time of that material after it's been deformed. And then what I was referring to in my talk is really about the electrical delays. And so, you know, with the capacitive type of approach, you have to wait for the capacitor to get recharged again, whereas the resistive approach, we can listen to it all the time and don't have to wait for it. I think that's where we found the benefit inadvertently.
Okay, thanks. Someone is highlighting this question for tactile perception. I didn't read it before. One of the methods that's mentioned in Veronica's work is to measure bump pit size and shape. But what about some objects which are not deformable? Do we measure shear force in that case?
Let's see. One of the objects which are not. So in the bump and pit example, a lot of our earlier work did focus on rigid objects. So these were 3D printed. They were not deformable. One thing that I think is an open question, and we've purposely not gone there yet, is what happens when the deformable nature and the properties of the object match those of the fingertip? Because we're relying on the fact that our fingertip will deform enough that we can sense some useful information from it. Let's say if you are now taking your deformable fingertip but manipulating water, right? That's like super fluid on the extreme of deformability. Now we can't get anything because our tactile sensors are not getting deformed. So that interplay between the relative stiffness of the fingertip that you are currently using and the object that you care about has been important, but we've not done any quantitative studies on that.
Mm-hmm. I think, I mean, when you were talking about water, I was swimming a lot, and one thing is you perceive water if you have in the non-glabrous skin, so in the where you have hairs. So there they deform differently with water, and you can perceive that. But it's really amazing. If you shave, you don't feel anything. You don't even feel the kind of where the water starts and where the air starts. So.
That's a great point. One thing that we have not looked into, but I know other groups have, like Meacher Hartman at Northwestern, is whisking above ground, but also whisking of seals underwater. And I think you might be getting, there's a microscale version of that with hair.
Mm-hmm. Very interesting. I don't know if our time is over or we can go on with questions. I think we can go on with questions forever. Cornelia.
I think it's over because, sorry, Chiara, it's unfortunately over because it's really lovely, great, lovely talk, both of them. But there's now an event in the TAC in the SMI, there's actually a tutorial, I don't know, there's actually a tutorial on from Tiago Marquez from MIT using the bone net architecture to simulate primary visual cortex in front of CNNs. I think that's probably of interest to a lot of people.
Yeah, sure. So let me thank again Veronica. It was very nice. Thank you.
Thank you for having me.
Yeah, really nice, really informative.
Yeah, thanks, Veronica. So we're concluding the day.
All right.
See you guys all at the tutorials or tomorrow. Bye-bye.
Yeah, so Tiago, we're holding the tutorials in the SMI Zoom session. Yeah.
Okay.
The link there. Okay, see you there. Bye.
Bye.